So in this lecture, we are going to cover two important aspects. First, 18 electron rule. Second, special metal carbonyl clusters. These are actually part of a unit or chapter, you can call it organometallic compounds. In this chapter, these are two very small topics, 18 electron rule and metal carbonyl. Now, organometallic compounds are those compounds where direct metal carbon covalent bond is present. Metal carbon covalent bond is present. These are basically organometallic compound. And in this field, these organometallic compounds are very much useful in industry, in different industrial process for mass production of different chemicals, mass production of polythene. For production of polythene, we use Ziegler-Natta catalyst. This is organometallic compound. There are few processes called Cativa process, Monsanto process, etc. For those processes, industrially, we use organometallic compounds. Some anti-malarial drugs are formulated using organometallic compounds. Even in our biological system, hemoglobin, vitamin B12, all these are organometallic compounds. So this type of compounds has a very special property that this bond can break very easily. But again, these compounds are somehow very much stable. So these compounds are very much stable as well as sometimes very much reactive. So for stability of organometallic compounds, so which organometallic compounds are very much stable, which is not stable, this thing is defined by a rule called 18 electron rule. So which organometallic compounds are stable, or which type of organometallic compounds are going to be stable, this is going to be determined by 18 electron rule. Now, for explaining stability of some special organometallic compounds, two rules are introduced. Okay, so our first topic is 18 electron rule. So for explanation of stability of few organometallic compounds over others, two rules are there actually. First one is effective atomic number rule, and second one is 18 electron rule. So this is very much popular, so we are going to skip that. This is very much complicated or difficult. So 18 electron rule is easier, so we are going to observe that. And this rule has actually two methods. One is neutral atom method, and another one is oxidation state method. Neutral atom method is also called covalent method, and oxidation state method is actually another name is ionic method. Ionic method. In oxidation state method, this metal carbon bond is considered as ionic, and in neutral atom method, it is considered as a neutral particular covalent bond. So in these two method, actually result is same, but we are going to learn it through neutral atom method. It is very much easier than oxidation state method. Now, in any organometallic compound where metal and carbon direct bond is present, so this type of compounds, or carbon, or any, you can say, any heteroatom. Okay, so we have metal and ligand, and metal ligand bond. Sometimes more than one metal is there, so metal metal bond is also there. So we have to learn electron count of all the species, electron count of ligands, electron count of metals, electron count of metal metal bonds. After that, we have to add them, and if we get 18, then it is following 18 electron rule. That means it is very much stable. So first we have to learn some electron counts. First, let's learn electron count of ligands. Electron count of ligands. Now, ligands, some ligands are neutral ligands, some ligands are ionic ligands. In neutral ligands, if n number of lone pair is present, actually ligand is going to bind neutral ligands. If ligand is neutral, then it is going to bind with metal through lone pair. So if n number of lone pair is present, it is actually donating 2 electron. So n lone pair is giving actually 2n electron. Okay, so 1 lone pair means it is giving 2 electrons. So electron count is 2. 2 lone pair, electron count is 4, like this. For example, CO, metal CO. Here this ligand is donating 2 electron, that means 1 lone pair. So this ligand has electron count 2. For example, another metal, my compound is ligand is ethylene diamine, NH2. So this lone pair is also getting donated, this lone pair also. So overall this ligand is donating 4 electron. So electron count is 4. For ionic ligands, electron count is equal to charge. Suppose Cl minus, electron count 1, O double minus, electron count 2, C4 minus, electron count 4, N5 minus, electron count 5, like this. There are some special ligands like NO. This has 2 different electron counts. Electron count, it can be 1 or it can be 3. If NO is binded linearly, then electron count is 3. And if it is bent, it is in bent form, then it is electron count will be 1. Linear means M N double bond O, like this, and bent means M N double bond O, like this. Okay, so linear 3 electron count, bent 1 electron count. So this is basically showing the electron count for different type of ligands. There are few type of ligands called bridging ligand. Bridging ligand. Bridging ligand means a particular ligand is donating electron to 2 metal center. Then chlorine is here bridging ligand. Now electron count for bridging ligand is little bit different. Here actually ligand is Cl minus. Cl minus is donating 2 times electron. Now Cl has 7 electron in valence shell. For being the Cl minus, from somewhere it has achieved 1 more electron from any source. From Cl to being Cl minus, it has gained 1 more electron from somewhere. It is not the electron of its own. Now when it is going to connect to a metal ion, first this lone pair is going to donate here, and second this lone pair is going to donate here. Now how many of electron of chlorine is getting donated? This is 2 plus 1, 3. Okay, not 4. 2 plus 1 equal to 3. So Cl minus, if it is breached, then electron count will be 3. This type of bridging is also called mu2 bridging. That means it is connected to 2 metal. It can be mu3, mu4, like this. Okay, so this is basically electron count system of bridging ligands. Okay, now it is all done for ligands. So this is basically ligand electron count. Metal electron count will be simply actually these organometallic compounds are mainly metals, are basically d block metals, and electron count of metal will be simply its group number. Okay, can you tell me, if the metal is iron, then what will be its electron count?
Group atomic number is 26, right, for iron? Okay, so I think
in a D block
8.
series it is in 6th position, and here group 1 and group 2
Yeah,
is additionally
2.
there,
So
so
8.
in 8. Okay, so electron count is 8. Similarly iron 8, so ruthenium, osmium, all will be 8. Okay.
Okay.
Okay, there are few ligands basically organic ligands. For them, organic ligand means ligand is donating its pi electron. For example, suppose this system. Now it is donating electron. If it is actually resonating, and this is actually donating to metal. Now, if I want to count the electron count of this system, it will be 4. Not because of 4 pi electron. It is because 4 carbon center is actually donating electron to metal. It is called hapticity. Hapticity. So hapticity is 4. It is nothing to do with the electrons. It is basically centers. One very common ligand is cyclopentadienyl anion. This is minus. This is aromatic compound. This is CP. In short form, it is written as CP. Here, if it donates its pi cloud to a metal, so total 6 pi electron. Total 6 pi electron is getting donated. But how many centers are involved? 5 centers. So electron count of this ligand will be 5. Suppose in any complex, it is written in such a way that, like this, only this bond is shown, it is donated to metal. Now its electron count will be, sorry, not like this. Now this negative charge is doing resonance. Okay, suppose in one example, it is like this. Resonance is shown like this. This 3 center is resonating, and this pi bond is not having resonance yet. Now this is actually donating to metal ion. Now electron count here will be 3, not 5, because 3 center is involved. 3 resonating center is involved. Okay, I hope you have understood this. Now tell me.
Yeah, but I have a small doubt there.
Hmm,
In that cyclopentadiene ion that you have taken, in that, as you told that the negative charge is in conjugation with the pi bond on one side.
hmm.
So, what about the other two carbon atoms on the other side?
At this
Like,
moment, this pi bond is not having resonance with metal ion. After that, after some time, it can happen that this pi bond and this negative charge, this 3 center is having
hmm,
connect is getting connected to metal ion, not this center. So at a time,
okay,
only 3 center is involved.
hmm,
So for CP ligand, electron
okay,
count can be 5. If nothing especially mentioned, then we have to count the full hapticity, complete hapticity, maximum hapticity.
okay,
It is 5.
hmm,
If it is shown like this, so it can be 3 or it can be 1 also. Okay.
okay.
Now,
So basically, we are restricting the resonance of that pi bond.
yes. And this particular system is so powerful that sometimes it distract the aromaticity of benzene ring. Benzene ring itself, in benzene ring, we know the very stable conjugation occurs, but it can happen that this 4 center is undergoing resonance and 2 center is not, and this is connected to metal ion, then hapticity here will be 4. It can disrupt the
Okay.
aromaticity of benzene. Okay.
Hmm.
Now tell me another question. Mm, what will be hapticity here, or electron count?
8.
8 simply, or it can be 4 or 6 or 2, but in this, it is
Mhm.
in this complex, it is 8. Okay, fine.
Yeah.
Now another thing remains is, or in our electron count, there is metal bond. In one metal bond, mm, yes, in one metal bond, 2 electron is present. So per metal bond, electron count will be 2 only. Okay.
Okay.
Now overall, if the compound is anionic, then the number of anionic charge will be added. That is basically electron. So that will be added to electron count. So plus anionic charge minus cationic charge. Okay.
Hmm.
So now I am writing total formula, the formula of this uh, total valence electron. The 18 electron, it is called total valence electron. Total valence electron, if 18, if one metal ion is there in the complex, then total valence electron will be 18. That is very much stable. If it is 17, it is not that much stable. If there is two metal center, then electron count should be multiple of 2, actually multiple of 18, so 36. Okay, that is
Hmm.
stable. If 35, it is not stable. Okay, total valence electron formula, we are getting that electron count of metal plus electron count of ligand plus anionic charge minus cationic charge plus metal metal bond electron. Okay,
Hmm.
now if I give you one complex, this is a very popular organometallic compound, name is ferrocene. Here let's calculate the total valence electron and understand it is very much stable or not. This system is going to uh, produce 5 electron count. This is
Hmm.
5 and this
Yeah.
is 8, total
Hmm.
18. Okay,
Okay.
now one more example, you tell me is it stable or not. Cp means this cyclopentadienyl.
Okay.
Molybdenum, chromium, molybdenum, tungsten, 4 plus 2 6, right?
Yeah.
Cl is actually Cl minus,
That's
sorry, not C,
CPU.
sorry, Cp5. This is
Yeah.
3, hapticity 3,
3.
this
Yeah.
is 3, this is 1, so total
Okay.
18, right?
5 plus.
Okay,
Yeah.
so this is basically
Yeah.
18 electron rule. So if one metal ion is present, then 18 electron organometallic compounds will be more stable than other electron counts. If more than one metal are present, then it will be, if two metal ion, it is 36, is 3, it is 54, like that. Okay,
Hmm.
now our 18 electron rule is over. Now our concern is metal carbonyl. One more thing, if uh, I have a formula of a metal, I have a formula of an organometallic compound, and it is said that it follows 18 electron rule. A particular compound formula is given,
Hmm.
and it is said that it follows 18 electron rule. Now, there is a formula of calculating total metal-metal bond. Total metal-metal bond. Uh, you can derive this in the previous formula. Okay, in the previous formula, if I want to count the total number of metal-metal bond, okay,
Hmm.
then I'm writing the formula and you can think of how the formula is coming. The formula is 18n minus total valence electron by 2.
Okay.
2 into, now if you solve this, 2 into total metal-metal bond, that means total metal-metal electron bond electron count. And if you add these to total valence electron, you will be getting 18n. N means total number of metal center. Okay.
Hmm.
And if you want to calculate the metal bond per metal. Suppose this is a system M. This is how these are ligands. Okay. So here the total number is 3. So total metal bond, using this formula we will be getting 3. But using this second formula we will be getting one metal has connected to how many metals, or has performed in bonding with how many metals. So it will be coming 2.
Okay.
Okay. The formula is 18 minus total valence electron by n. Okay.
Okay.
Now I have given you one question. The question is Fe2Co9. You have to calculate
Yeah.
the total metal bond and metal bond per metal. This question I am solving. The second one I will give you to solve.
Okay.
So in this particular system, total how many metal bonds are there, I don't know with the formula. If the structure was given, then I can say. Okay.
Yeah.
So here the total metal bond will be 18N. That means 18 into 3. Okay. Minus total valence electron means 3 iron means 8 into 3, 24. Plus
Okay.
12 into 2 per carbonyl CO2. So 24. Okay.
Okay.
By 2. What?
So 54 minus 48, 3.
3. So we have to derive the structure actually. We have to know the structure. This is 3. Now metal bond per metal. Now calculate this. It's simple. TVE we already know.
Yeah. Plus 6. No, sorry. Total valence electron. 3, 16. 2.
2. So 2 and total bond is 3. Now with this information, we have to apply our logic that how the 3 iron centers can be arranged. So total 3 bond, and per metal there is 2 bond. So the possibility is metal. These are connected like this, isn't it?
Yes.
So the metal cluster, the arrangement of metals are basically trigonal planar. Okay.
Okay.
Now we can assume the structure, it should be, now there are 12 carbonyl. So it can be divided like this, each metal having 4 CO. Okay. So we can assume this may be the structure. But actually it was found that in that particular compound, the arrangement is like this: iron, 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 CO, 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 CO. 2 carbonyl is basically bridging carbonyl. That means that CO, this lone pair is donated to 2 metal ions. Okay. Electron count is 2. Another carbonyl is similarly bridging. So how many carbonyls left?
4 plus 2, 6 done. So 6 more remaining.
3.
3 and
Okay.
3. Yeah.
Actually bridging gives the system a better stability. Okay. Actually this bond, if the bridging is not there, this bond is actually bond length is higher. Okay. So it compact
Okay.
the bond length, therefore more bond energy releases. Okay. And again this when it is bridging, then one carbonyl is making actually this two carbonyl. If it was not breached, then these two carbonyls separately would making two sigma bonds only, but in the bridging it is making four sigma bonds. So these are the factors why the systems try to bridge. Okay,
Hmm.
so two carbonyls are found bridging experimentally. It was found with the um, we found the evidence in stretching frequency. Stretching frequency, we know the formula. Stretching frequency, more strong a spring, okay, more will stretching frequency, right? A
Hmm.
stronger spring will have more stretching frequency. So if we consider bond as spring, okay, this carbonyl, actually this carbonyl is C triple bond O. Here, if one lone pair is donated to one metal only, the carbonyl stretching frequency is higher. But if it is connected to two metal, this stretching frequency reduces. Experimentally, it is found that the stretching frequency of bridging carbonyl is 1850 to 1750 semi-inverse. But
Okay.
the terminal one is 1850 to 2120 semi-inverse. So in IR spectroscopy, infrared spectroscopy, in this compound, if we found a particular peak at this range, we will get confirmed that there must be bridging carbonyl. And with the intensity, we can tell that there may be two. Okay,
Hmm.
so this is the structure. Now let's move to similar compound, but iron will be replaced by ruthenium of the same group.
Hmm.
Iron will be replaced by ruthenium. So Ru3CO12. Okay. Now here the ruthenium bond is much more longer than iron bond, isn't it?
Yeah.
So if the bond is longer, then there will be very much strain on this bridging. If the bridging is going to occur, there will be very much strain on this carbonyl.
Hmm.
Okay? So this will not occur. So the bridging will destroy, and simply it will be 4 4 4 carbonyl. This will be structure.
Okay.
It is osmium if the similar kind of structure. Okay,
Hmm.
so
Okay.
three compounds we have done. Next one, CO4, cobalt 4, carbonyl 12. Total metal bond you can calculate, and it will be 6, and metal bond per metal it will be 3. Now we have to construct the structure by thinking that how a geometry or how a structure is symmetrically possible, where every center is connected to three metal, every center has three bond, and total number of bond is 6. If you do
Hmm.
some trial and error, you can find that the structure must not be like this, must be like this,
Hmm.
like this only. Every metal center has three bond, and total number of bond is 6. So this is basically the structure. Now here also, this is basically the bond distance is low in this is cobalt. Okay, so here also bridging is possible. If bridging would not occur, then we would distribute the carbonyl equally, so 3 3 3, isn't it?
Hmm.
But the bond distance is low, so there can be bridging. Actually there is bridging. The actual structure is cobalt, 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 cobalt. There are actually three bridging. This is a very symmetric structure. Three bridging. And this center will have one CO. This cobalt will have one CO. So it's one CO. How many cobalts? How many carbon monoxides or carbonyls are remain? Six.
Mm,
So
yes,
two,
yes.
two, two. This will be structure. Okay.
Okay.
Now
In the 3D plane, will the cobalt, like the central cobalt atom, will it be backward or frontward like that?
tetrahedral. This is actually tetrahedral structure. Okay. This
Okay.
is backward or front, whatever you can consider. I have drawn it. It is in back. Okay.
Mhm.
That's tetrahedral.
But one more doubt. Why can't we have a bridging carbonyl between the central cobalt and the cobalt at the edge?
Central cobalt and
Yeah,
the edge.
yeah.
This is actually same thing. You can replace this with this. This is actually same thing. In tetrahedral, all the structure, all the bonds are similar. If you transfer
No,
this
but
to,
hmm.
if you transfer this bond to this, there will be nothing difference.
No, not transfer. I mean that, like, why not add three more, like bridging carbonyls? Like the
Uh,
already existing ones, let it stay. I want to add three more bridging carbonyls to the other ones.
Actually, these type of structures are found, and later we have tried to explain its stability by this 18 electron rule. Okay, so this
Hmm.
is the in hand evidence, and
Okay.
from this evidence we are trying to make some formulas, etc. In science it's work like that. First you have received one observation, later you
Hmm.
are trying to predict that similar kind of structures. So thus 18 electron
Okay.
rule came, a tool for explaining the stability. So for something it works, something it sometimes doesn't work. Here three bridging
Hmm.
stability, maybe for steric hindrance or something, there may be any reason. Okay, specifically I don't know.
Okay.
So it is found that there are three. Okay, now
Okay.
if we replace it to cobalt, then we have rhodium, Rh4CO12. Then it is found that this is actually similar kind of structure. The bridging has not disrupted. Okay,
Okay.
but next one, iridium, cobalt, rhodium, iridium, Ir4CO12, again all disrupted. That means all carbonyl are terminal carbonyl. So it will be like 3 3 3 3. Okay,
Hmm.
like this.
Okay.
So uh, till now we have discussed six compounds. Out of this, bridging CO we have found Fe3CO12, cobalt 4CO12, and rhodium 4CO12. Right,
Hmm.
in these three only the bridging can occur. Another compound, another metal carbonyl, Fe2Co9. Okay, the structure is Fe. It is a particular compound having three metal carbonyl. CO, oh, sorry, CO, three. This is the structure. Okay.
Hmm.
Sometimes what happens, if temperature is higher, then their vibration in this bond is increased. So sometimes this two metal ion is going far away. Whenever it is going far away, then the bond is disrupted. So it is found that in very high temperature, the bond is broken and all is terminal. Okay.
Hmm.
Okay. Last important metal carbonyl compound is our octacarbonyl dicobalt, CO2 CO8. In organic chemistry, we have done this reagent. Okay, try
Mm.
to remember in which process we have used this. Okay, try to remember in one process from alkene to carbonyl. It was used. We have used this. Okay, so here two type of structure is possible. One in liquid phase, the structure is different. In solid phase, structure is different. Liquid phase, it is very simple. Cobalt, then 4 4. Okay, the structure is
Mm.
simple. But in solid phase, the structure is CO double bond O double bond O CO. This all the structures you will find that everything 18 electron rule is followed. Okay, here not 18 into 2, as 2 metal center is there. So overall 18 electron rule in every case of metal carbonyls, this metal carbonyl clusters, uh, 18 electron rule will be followed. And one last thing I want to say, that in that CO4, in that Fe3CO12, what happens?
Mm.
A kind of shuffling happens. Shuffling means sometimes this carbonyl is getting transferred to this, and this is getting converted to this. Okay, this is
Okay.
this is called flagionality. Flagionality. In high temperature,
Mm.
it will be more prominent. This exchange will be more prominent. So it is found that uh, temperature above 123 Kelvin, metal bond length, sorry, metal carbonyl bond length will be same. Above 123 Kelvin, metal carbonyl bond length will be same. As all is flagional, then this bond length will be, these all are exchanging in a rapid fast way, so all bond length will be similar. But if we freeze it, it will be not similar, it will be different. But above
Mm.
123 Kelvin, due to flagionality, then the these bonds seems to be similar. Okay, all bridging carbonyl, metal bridging carbonyl and metal terminal carbonyl bonds are similar above 123 Kelvin. So these are all the things in 18 electron rule and metal carbonyl clusters.